Cool. Hello, welcome everyone. This is the second compiler's reading group. This time we have a presentation from the paper Urbit, a solid state interpreter by Curtis Yarvin, Philip Monk, Anton Dwenden, and Raymond Pasco. Today, Ray would like to lead, and so I will take a back seat, and I'm going to enjoy the show like anyone else. Ray, you have the floor.
All right. Yeah, so that's like a pretty odd paper, definitely. It covers a lot of things in not too many pages, and sort of jumps from topic to topic quickly. It's slightly outdated as well. So the main thing I'm going to focus on, at least to begin with, is the Nock virtual machine, which is it's a simple combinator machine. It's used as the like the compilation target for a higher level language, and to my knowledge, it's like the most the main like practical example of something that works by combinator reduction and just rewriting rules that exists. So we have let me pull up the actual current version of the spec. If you looked in the paper, there was a listing for a Nock spec. Despite all the protestations about how it's never going to change in the future, it actually has changed in one way. The current version, which is version 4 rather than version 5, is slightly simplified and slightly simplified in terms of the expansions, and adds one opcode. So hints have been bumped up to 11. Let me put it in the actual terminal. Okay. Put it in the text editor. That's enough. There we go. Okay, so yeah, this is written in this sort of strange bespoke pseudocode. The important parts are the parts that have a star on them. So those are actual opcode reductions. And I'm going to go along and do examples here of each of these opcodes. So most of the time, when you see combinator languages in CS, there's something like S and K combinators, right? They're attempting to provide a very minimal minimal description of universal computation that you can prove theorems about, and so on. The goal of Nock is not that. The goal is to provide sort of a useful low-level VM. So the first thing about it, which is not exactly part of the spec, is the definition of the noun data structure, which is the only thing that it operates on. So we have all we have are just const cells, basically. So we have atoms, which are just they're just natural numbers. There's not like a size limitation on them. They're just any natural number. So this is an atom. This is an atom, and even very large ones. Well, very large ones might crash, but that's 2 to the 2 to the 4, by the way. So the Bex is 2 to the X. So even very large atoms, but not large enough to like actually overflow memory, are just atoms. That's just an integer. And then we have and then we also have cells, which are just a const cell. The head is a noun, and the tail is a noun. So that's the data structure we're operating on. And we write them with these square brackets. This is just the associativity rule. So if we write three things in square brackets, it means it associates right. Then we have we actually have I'm going to add there's actually an opcode 12 as well. So there's 13 and possibly 14 instructions. The way that the Nock actually operates is it actually operates on pairs. So you have and this executing in the REPL is just direct Nock instruction. So you operate, you have a pair. You can view it as just a const cell of two things if you like, but it operates on pairs. It operates on a subject, which is the entire environment that's available. Because remember, all we have is these rewriting rules. So anything that we do computation on has to be in the combinator expression that we are reducing. And so you can see all these A's here represent the subject. So in this spec, it's the head. Here in the REPL, I just specified as the first argument. So the subject, the atom 999, do the formula, say 01. So that's how I'm going to be executing examples here. The opcodes are in order. The first two are 0, read from subject, and 1, constant. Everything else you can see in this rewritten version of the reduction rules, you see a lot more stars. They just indicate which sub-expressions actually get evaluated versus which are like read and used. So they generally every expression, like they might contain other things and resolve recursively, which is what the stars indicate. Here we have like star AB, star AC. This means that the evaluation will just proceed recursively, evaluating first A, B, whatever A and B might be. If something like fails to validly match a rule, it's just a crash. Which are they're written weirdly in this like for example, fast A equals fast A syntax. It doesn't mean that we spin infinitely. It means that spinning infinitely is morally indistinguishable from crashing. What we actually do is crash. So we have the read from subject and the constant, our opcode 0 and 1. Zero reads by tree address, right? So if we have 0, 0, tree address 0 is invalid. Like the formula 0, 0 is the standard way to induce a crash, right? So if I jump ahead a bit and compile this zap, which is a high level language Hoon syntax for crash here, you see it compiles to 0, 0. 0, 1 is like the entire tree. And then the head is 2, the tail is 3, and it proceeds recursively like that. So the head of the head is 4, the tail of the head is 5, and you see I put 4, 5, 6, 7 in there. So if I get 6, I have a 6. This is just a generic way that you can address anywhere in a binary tree, and it's used quite a bit because the only other way to have a value for the other opcodes is with opcode 1, which is just a direct constant. So anytime any if you look at these, you'll see that they right, they're going to evaluate some sub expressions, and all of these are going to bottom out in some zeros or ones. As far as these goes. So then the next opcode 2 is just eval, and you can see you can see the reduction of it is pretty simple. You just you have your formula is like two BC, so some formula. And you evaluate the first one that gives you the subject, the new the subject that you're evaluating against. Evaluate the second one that gives you the formula, and then you evaluate the whole thing. So, for example, using 999 as the subject, do a very simple two. Say 1, 1, 2, 3. So the subject will be constant 1, 2, 3, and then 0, 1. Get the whole subject. All right. What am I failing in here? Oh yeah, I have to add more layers of because I have to evaluate the whole thing against the old subject. So it would actually look like, and let me borrow the compiler. Yeah, I have to add yeah, 1, 1, 0, 1. I can't just produce the formula. So that's eval, and then the other things are just useful primitives that we're required to do useful computation. So 3 is just test if some noun is an atom or a cell. This is like the basic branching operation that's provided. 4 is increment an atom by 1. This is the basic arithmetic operation you provided. So with those and eval, and 5 is just noun level equality. So you just compute both. You like fully evaluate both arguments, and then you gave true if they're equal and false if they're not. So with that, you have a very minimal sort of specification that does arithmetic, and it has arithmetic and branching and a test. So it has that up to that is your fully like Turing complete model of computation. It might seem like a very very weirdly streamlined and impoverished one, which it sort of is, because the only arithmetic operations provided is increment. The only test is testing if something is atom or a cell. It's only like the large instruction set practical combinator machine compared to every other combinator machine that exists, because they're all things that try to express computation in like one iota combinator, or 3 SK and I combinators, or so on. And the operations are meant, rather than being super theoretical operations, to correspond to actual things that you want a compiler to target, rather than having to be very Baroque expressions. In fact, all of these do have a direct equivalent in the high-level language tune. You've seen the one for 2 already, because this .tar direct evaluate Nock thing just is just that. But you also have like here I'll invoke the compiler again. Like any just direct expression is evaluating to a 1. Any reference to a name, ABC, or right. Any reference to a name is have to get around this compiler optimization. Yeah, any reference to a name is going to turn into a 0 or potentially a 9. Here in a bit. And we have primitives for these, most of which we do not actually use in code, but you can directly increment an integer using one instruction if you want. Or like 2, 3 is not and not a cell, but 1, 2 is. So those are the direct instructions. Oh, right, inequality. There's syntax for equality, but like they're equal. These are not. That's full equality on entire noun. There's not like any sense of indirection or pointers. There certainly are in the VM, which I'll get to. But at the level of semantics, there's just only large binary trees. So then we have the remaining opcode, which are offset by a bit, simply because in theory they're just implementable as macros over the first ones. And earlier versions of the spec, like the one in the actual paper, did implement them as macros over the opcode, which is kind of tricky to read. But they're all fairly simple. So this monstrosity is just if then else. So A6BCD is this is some expression that has to give either 0 or 1 for true or false, and then you have a true branch and a false branch. 7 is with subject. The 7 is like the much more natural thing than 2 in terms of actual code. You just give the formula directly rather than giving a formula which evaluates to a formula, which is excessive metacircularity that's only necessary in specifying Nock and writing the compiler and so on. Good. Just you have something that gives you a new subject, and then with that subject, you execute the formula in C. 8 is the perhaps more common push on subject, which is rather than giving you a formula which you then use as the subject for some other formula, it just you have the first formula B just gives you something new which you push on the subject, which means you constant it with the old subject. So your new thing is in the head of the new subject, and you're in the tail, and the previous subject is in the tail. Like with the subject 999, we have 8 1 1 2 3. So that's push on subject, just constant 1 2 3, and then for 1 the subject. So I just pushed constant 1 2 3 on the subject. This formula could be anything, so it could be 0. I could just get the subject again, duplicate it, push it on itself. 9 I'll get back to in a second. That's the calling convention. 10 is something that was not in the paper. It's a more recent addition. 10 is just replacing a subtree. So previously the compiler would use this rule, autoconst, which just means that if you give a cell of 2 formulas instead of a formula, you get the cell of the results. And it would use this to edit some noun on the subject. Like if my subject is 1 2, and I want to replace the head of the subject with 999. I would have had to do like 1999 03. In order to do that, the compiler would have to output things like this. Now there's just the direct. I can do 10, and then I have to give the axis I'm replacing and a formula for the new thing. So replace that with 999. This is the argument. I mean, that's actually what I'm getting. So now there's an opcode for that rather than the compiler having to generate things, which get somewhat complex. Like here, the version with 10 is actually larger. But if you're going deep into a noun, which you usually are, and you're replacing something at axis like 36 or 250, then it would result in kind of very large expressions. But here you can just provide something. I change that to 3 to replace the tail with 999, or I can do a more complex noun. So that's 10. 11 11 is a bit special. 11 is hints. So hints are it's almost just discard the hint part and produce the non-hinted part, and that is in fact how it works if the hint is an atom. Because then you can just discard the hint. These are just hints to the VM, which are very important because, like I said above, the only arithmetic operation, for example, is increment, which means that subtraction, for example, is a very complicated algorithm if you do it naively. What you actually do is you provide, the VM provides subtraction for you, and you use this hint to tell the VM that it should actually be invoking subtraction. The caveat with hints is that if you use this dynamic hint where B is still just some atom, right? It's still just the name of the hint, some word that the VM can read. But C is an actual formula, and it does have to be computed because it could be a crash. So like any subject, I do. 11. This is just equivalent, but if I have a formula, it might crash. But if it doesn't crash, then its product must be discarded. That's just a dynamic hint. Okay, so we'll go back to the interesting thing now, which is 9, which is the calling convention. So this is sort of where we get the distinction between code and data here. A 9 BC, in this case, B is actually not something cell-evaluated, right? It just appears here, not inside any starred expression. B is a tree address this time, like N0. This is how we take something from the subject that happens to be code rather than data and evaluate it. So first, I'm going to just give an example. Like, so 40N is, of course, right? This is just the formula for increment something on the subject, right? So I'm going to remove the extraneous brackets because they associate in that direction. We have 1000. But I'm giving that as a formula and say that I want to have it on the subject. What I do is construct something like this, right? So I have this noun. We call them cores. By convention, they're just their cell. The head of the cell is some number of formulas. In this case, it's exactly one formula, but it could just be any tree of formulas with known. The axes of each formula in them are known to the compiler. And this is how they're given names in the high level language, which are turned into addresses by the compiler, just like most compilers do with things. So you have the head is formulas. The head of the cell is formulas. The tail is another cell, the head of which is a placeholder argument. So in this case, increment works on atoms, right? So my placeholder is going to be 0. And then just arbitrary context, which is usually the entire subject where the core was created. So this is like your environment. Since this is a full combinator reduction system, everything that you reference has to be physically present in the noun that you're running a reduction on, right? So this is where a core brings its entire calling environment around with it in here. I'll just change it to 999, like I've been doing to indicate that it's sort of arbitrary. This is also arbitrary, but it has to be the right shape, right? Because I couldn't put 1, 2 here because you cannot increment 1, 2. Well, Nock is basically just untyped. The Hoon type system is what would detect this. So 9, then 9 needs to get some. So the first argument is an axis. So in this case, it's axis 2. Axis 2 of what? Well, in this case, 0, 1, the whole subject. It would probably be 0 something else. So this means take the get the noun from this formula, which in this case is 0, 1, get the whole subject, so this noun. Find the formula at axis 2 of it, so in this case 406, and compute that formula using the entire core as the subject. So what they're going to do, well, with this noun as the subject and 406 is the formula, first it'll get 06, which is 0, and then it will increment it. So you should get 1, and you do. The calling convention is the combination of 9 and 10. So you have 10, slide this argument for now, and then 1. And then what the calling convention is always to replace at axis 6 with, say, 1, 1, 2, 3. So you see, if you look at this step by step, what's actually been done is delete the outer 9. I've taken the subject. I've replaced the argument placeholder, like I said, with something else of the same shape. In this case, 1, 2, 3. And then I've used 9 to take this core, and 9 2 on it means to execute the formula axis 2. So that's equivalent to, in this case, well, in this case, taking the whole thing. So I can just do that. And then using the formula at axis 2 on it. This is how you carry around both code and data at the same time. Of course, I actually had the one that was replaced, so that. So you can see how, like, if I used if I use all of these together, I can get fairly complex things. Like if I do with subject 1, 2, 3, if subject is equal 1, 2, 3. Wait, let me give it a name. Something like that is possible. But it turns into this thing with like a 7, a 6, lots of zeros and ones at the leaves, like I said, and so on. So that this is this then is the whole thing. I did mention there's an operator 12. Indeed, there is in user space. So every time that we actually evaluate Nock in a running system, it's a few layers of virtualization. One of the things that the virtualization layers do is add operator 12, which is like, it's a user space hinting operator, basically. No 12 ever reaches the actual C virtual machine that all of this is ultimately running on. It's all just it's like a hint escape for the user space virtualizations. And this is sort of transparent virtualization, which is pretty easy to do for our VM. So naturally, this is like obviously, or I hope mostly obviously, this is like a Turing complete computation model. It's mostly not that obscure. Like the opcode, primitive opcodes are recognizable things to programmers, like, if then else, or call a function, so on, or like a test for equality. Compared to sort of very weird things, like if you're trying to build computation on some iota combinator. The data structure is the const cell, which it's not like a universal data structure. Like you don't get C arrays. You have to rely on the VM to sort of turn some of these const cells into more efficient C arrays when it suits, and other things like that. So it's a universal model of computation with benefits and drawbacks. You noticed before that I was able to like exponentiate things without taking a huge amount of time. Like if I add, some very large numbers, or even like just some very small numbers, this doesn't like take appreciably longer than adding 1 and 1. I can decrement something without it being O of n. This is because VM supports all of this. If I go into this is the Hoon language compiler. I just want to point out that it like if we have addition, the definition of addition is actually this this loop where it just decrements something, and decrement is already O of n if you execute it naively. Then increments the other operand and does it until the first operand is 0. Decrement is just this loop where like we have some integer b, and we just keep checking if a is equal to b incremented, and then just incrementing b again. So of course these are actually in the VM, these are just GMP big nums. So like the what is a noun actually in the VM level? Basically, it looks something like this, right? To simplify. So we have VM is 32 bits. Like some like OCaml implementation, for example, the high bit of this is a tag bit. That means if the high bit of this 32-bit integer is 0, then it's actually just an atom. It's just a 32-bit word. It's only if it's 1 that it's a pointer, and it might be a pointer to an atom or a cell. And if it's an atom, it's a GMP big num, because atoms are just any natural number. In general, we use GMP big nums for things, but if you wondered why like the paper and so on use so many of these 4-letter things, because it's 7-bit ASCII, and so 4 characters of that. Met3 means measure by 2 to the 3 size words, so measure by bytes. They all fit into 4 bytes, which means they're all direct addons in the 32-bit VM. In its defense for being 32-bit, the project was started like many decades ago. But a 64-bit VM is probably better for most purposes. Like an important thing about 64-bit machines is that they only actually use 48 bits of any pointer. Like there's no CPU that supports addressing more memory than you can address in 48 bits. So rather than having to do something like have your memory and have 1 tag bit for optimizations like a direct atom, you get sort of a lot of tag bits for free, or at least you get them for free until advanced CPU generations don't exist yet, start using more high bits of a pointer, in which case I guess you'd have to your virtual memory would be limited to 128 terabytes, or however much you can address in 48 bits. I think it's 128 terabytes. It looks like that. And then there's a hash, which could be any sort of fast hash table hash is good here. The actual Urbit code base uses Murmur3 implementation, which it exists both as mug and hoon. So you have mug any noun. I'm doing it at the hoon level here, but like 1, 2, 3, 4, whatever. Let me print this as hex. You always have some fixed 32-bit hash of every noun. This is how we carry around these like giant environment trees and so on. In the VM, everything is actually stored by hash. So there's it's very common to have, like I showed you 10 already. So like if you have some very complex noun, like my current subject, for example, is an extremely complex noun. You can see just a lot of things. Most of this is type information. Like if I wanted to change something deep in this, uh, that would be. I changed this bit here, by the way. So that's just syntax for taking the whole subject, which is dot, and replacing something in it by name. So naively, you would expect that this would involve like copying extremely giant binary trees around, but it doesn't, because the indirection is through this hash, which is it's sort of lazily computed in every noun. And like the actual struct noun in the VM is going to be a bit more complicated than this, but these are the important parts. Things are allocated using a loom-based allocator, which is a pretty bespoke thing. It's just an allocator that you can nest other allocators inside backwards. The idea being that you have like the stack at the top growing down, and allocator allocations at the bottom growing up, as you would expect. But you can nest second allocator in the opposite direction inside of this. The idea is that you allocate things into the outer allocators stack frames by allocating them with malloc on the inner thing. So you can produce complicated things. You produce complicated nouns on an inner road, and then you just sort of give them up as stack variables to the outer road. So given that, we have this this sort of simple and sort of untyped thing that serves as like the low level compilation target for our machine, right? So the question is, how do we get from this to a high level language? And that's what the Hoon stuff is about in the paper. The paper was written at kind of a turbulent time in Hoon development, so a lot of it is not equivalent to the syntax that you would use today. But briefly, you have any word that you see is an identifier. There's no reserved words. Instead, syntactic constructions are just digraphs. This digraph is Barthes, which is defining a function, right? And you have that. This is just syntax for increment, which is Nock 4, as I've said before. Like this is you can see that this definition scrolled by, and the actual definition part of it is all the way up here. That's because whenever you define like a function or something, or any core, which is any noun containing code, the definition of it takes the entire the entire subject where you defined it becomes part of the core, right? So we have this is the standard library core, which you see repeated many times up here, right? You see it here it is, here it is again, here it is again. This is going to be repeated a great deal of times in any actual subject that you find, because this is the standard library. So even when you're doing your base definition of something in like a new module or whatever, you'll have this as your subject. So I'm using this. The standard library is called Zeus, so I'm using this syntax to use just Zeus as the subject. I define. function taking an atom A, incrementing it, and I'll have much more manageable things. So the syntax looks like this. You have this is actually displaying the type of it, not the not like data about it. You can see it takes an atom, and it has its context just this whole standard library version 140. So that's all well and good, but say that rather than taking an atom as the argument, it takes a cell of 2 atoms, right? Well, this has failed the type check. The question is, how does the higher level Hoon type checker work on top of this sort of untyped, just a natural number only VM? And does it have things more complex than atom and cell? The answer is yes. So the way that it works, so dot is something that compiles to 0, 1, and here I'm using mint, which means just call the compiler, the entire compiler on some string, and produce both the type and the compiled code, right? So I mint this, you'll see that it fails to compile, right? Because when I'm calling just the generic the compiler generically, what I'm actually calling is to call the compiler, you have to provide a goal type, which is the type that you want the expression to nest in. Nest meaning just be the same type or a subtype of. So if I expand this, what I'm actually doing is ream being the reader or the parser. So I'm doing that. If instead I knew already that the type of the subject were atom, then the type checker would the type checker state machine would start with a subject type of atom, and then that actually does compile and type check because it knows that the type of this expression is atom. So like the top and bottom types here are noun and void. So like if I have a goal type of void, nothing is ever going to compile. At the top level of compilation, you have a goal type of noun. You might have a smaller one at other things. So the way that the type system actually works is it only infers forward. It doesn't ever try to unify terms. It's like you'll have some primitive thing like 1, 2, 3. You know that this is an atom. Specifically, it's an unsigned decimal atom, which matters because like you have to coerce twice to coerce it to like a signed decimal, for example. But you only have to you can auto convert between like unsigned decimal and unsigned hex. So this is just like an extra safety feature on atoms because atoms are used for a lot of things. Like this is an atom. Like this is an atom. Like this, the current date and time is an atom. There's a great deal of atoms here. One other thing you can do with atoms is like if I have ABCD, right? That's something. If I use this percent syntax, that's ABCD with the constant types. That type is just only exactly that. So that's like our how we do symbols and so on, right? The percent ABCD is has type percent ABCD. And it also has value percent ABCD. You can also do like the empty string looks like that percent $sign. You can even do things that aren't just 7-bit ASCII with the like identifier valid symbols. Sort of anything can be given the constant type of itself. So how do we use this then? So we can take these like atom types, more or less, which are just some generic atom represented with at, like can use these backticks to cast, so I can just cast that to generic atom rather than unsigned decimal. Or I can like double cast it to a string. Now we have this curly brace. In the cubical versions, which are just constants with types of themselves. So in addition to these atom types, we have cell types, clearly. And this is how we get product types in our language, right? Because the type of we have like this. This is two constants, but we have more interestingly, like we have two atoms, right? So that's how we get product types in our language. And then finally, sum types. These are not like MLABTs, and they don't litter constructors everywhere. They're literally just the sum of two types, right? So if I have present ABCD as a type, or ABCD FGH, that's just the sum of two types. So that's the type either ABCD or EFGH. You can always forget type information about something, so I can always cast to this type any percent ABCD. Now I've forgotten type information about it, so like I've relaxed the type. You can always use a cast to forget things, and you can always refine by pattern matching. So in this case, with my subject as some value named value, right? If and this is the pattern matching operator, so if give the type that I want it to be in, the true branch 1 2 3 and 4 5 6. Okay, so that's simple enough. Within each branch of this if, do this again. Here I'm just using an invocation to get the type, the type as a noun at runtime. So if I am going to have both the true and false branch be that. All right, yeah, I have to use a plus there, because I need some things from the standard library to actually use that. Okay, so you see, yeah, in this branch, because it's branching off of a pattern match. So then it knows in the true branch, which it followed, that the type was that. Since we have proper type subtraction, it also knows that in the false branch, that it was the other thing, right? That its type was the rest. So if I had I had some very large sum type, right? A B C D E. It was E, and then if this is A. Okay, and since we have proper subtraction on sum types, it knows in the false branch, which is the branch we actually followed, that the type of value is either B, C, D, or E. It knows it's not A because we already pattern matched that away. And so there's a macro that looks more like a switch case statement, perhaps, or like a series of pattern matching expressions, which is this this switch thing, and you just and just provide various things that it can pattern match against and values. This is just a macro. It just expands to a bunch of nested ifs with something special at the end. So like if I compile it, it expands to something with a special lost at the end. So you see this mint lost error means that it wasn't that my patterns were not exhaustive over the entire space, because here, remember, I'm just compiling, and by default the compiler has a generic noun as the subject. And clearly a generic noun minus this one constant is not exhaustive over everything. So that's invalidly non-exhaustive, for example. So given that we have sum types, we have product types, we have the ability to forget type information by casting, we have the ability to refine type information by pattern matching. So that gives a full type system. The only thing that's somewhat tricky are recursive types. So like, for example, there's like you can have like a list of atoms, for example, right? And you can it's like a fully typed. You can see it casts a list. The squiggly in front is syntax for a list. This is, it just means that, right? It has a null terminator. So as a list of atoms, you'd be wondering what the type of that is. And the pretty printer is going to try to hide it from us. All right. See, as like written before I cast it, it has this more refined type, right? It's 3 atoms and a null terminator. 3 atoms and like a cubical nil, right? Here I've forgotten type information, but I did define a convenience type here, and you can see this outputs quite a lot of stuff. So what is it actually outputting? The main reason it's quite a lot is because it's including the type of an AST in here. So the trick for recursive types is they actually just include the here it is. At the very last thing, you have the actual definition of a list as an AST, which is sort of lazily expanded, included in the type itself. So like recursive types can get very large as nouns, which is why there's such an aggressive pretty printer that I have to manually bypass in order to show them. Especially since every time you define something, you end up with you're carrying your entire context around with you inside that noun, which is perfectly fine from a memory perspective, because you're just you're not allocating. You just have a tail pointer to something. Something which exists by hash in the VM. But when you want to pretty print it, it turns out to be quite expensive quite expensive in terms of screen real estate, as well as time, actually. It takes a while to recurse through these gigantic nouns and attempt to print them. So for that reason, there's a very aggressive pretty printer. And the types of cores, like if we have like the simplest possible core is just this zero-armed core. And as a noun, it's just the cell of 2 zeros, right? Everything about it that makes it a core is type information. If I have a slightly more complex, now it has one formula in it called A that just produces 1, 2, 3. Now you see the more like a more familiar core shape, right? It has the head of it is some formulas, in this case one formula. The tail of it is a context. This is not something that takes it's not a core that takes arguments, so there's not two things in there. If I turn it into a core that does take arguments by providing an argument, okay. So then this is the placeholder argument. It'll get replaced by some Nock 10 instruction if we ever call it with an argument. This is the whole calling environment, which I manually replaced it with nil here. But like with subject, use my placeholder 999 instead. You know, this formula A could be just like give the whole subject 0, 1. Have two formulas. Yep. Now I have two formulas. So what the compiler the compiler is what keeps track of names, right? Names are resolved very simply. So like if I have the subject a equals 1, a equals 2, name A, what do I get? I get 1. If I have it's just a left first, depth first tree search on the type of the subject until it finds something that has that name. It won't go inside something that's already named. So if I slap a name on this, now it's 2. I would have to do A inside N. The like name spacing dots are backwards in Hoon from basically every other language. It's A inside N, then N inside A. So here, like that, back up here, I now have two formulas inside my core. So A is clearly just it's constant 1, 2, 3. So that's clearly this. B is a formula that calls A. So in that case, you see it actually has a 9. It's 9501. So it's calling at axis 5 of the whole thing. So if you recall, like 5 is 5 is tail of the head. So it's finding at axis 5 tail of the head. In this case, the head is this whole like tree of formulas. In this case, it's just a 2-leaf binary tree. And then the tail of it is 1, 1, 2, 3. So 9501, just take the whole core, call it axis 5, and that's 1, 1, 2, 3. Tree addresses are they obviously get very large in terms of the actual standard library. For example, if I take the add function, again, go back into the compiler. So add is very close to the beginning, so it's not going to have a huge amount of context to it, right? Add itself is just something that takes 2 atoms. I take the formula from add just as a noun. And see even it is calls some relatively large tree addresses. Like here, it's actually calling decrement here. So that's tree axis 2398, which is quite deep into the tree. You can see, yeah, the only thing that it calls out to is decrement. So even in this, it's pretty large. And some of these have quite a few arms, so they're going to have very large tree addresses. But in general, like this is there's no need to have a symbol table or anything like that. You just compile everything down to a relative tree axis in whatever the final noun ends up being. Yeah, and given that we have all of the basic building blocks, there's obviously a lot more like syntactic refinements, type system refinements. Like you can for example, there's function subtyping, so the type checker knows how to be like contravariant in function arguments if you tell it to. So there is a lot more complication than this, but this is actually more than sufficient to have a simple system in which you could have implemented the rest of the system. Now that's not actually the order it went in history. It's just an order that I felt would make sense to present it in. Because like when you're bootstrapping a system like this in history, in reality, what there was sort of a in C, just sort of a proto hoon. And some manually written Nock, although like any extremely low level thing, like it's more cumbersome to write manually than say x86 assembly or WASM or something. Specifically because specifically because it's a tree and there's not like good tree editors out there. You can get a bit of help. Can get a bit of help from the REPL itself if it already exists. Oh, right, that's not right. By having it like pretty print things for you. So rather than having to glance over that and see which things are opcodes and which things are arguments, it's pretty printed it for me. I've just cast it to the Nock type, which is something I didn't even get into. You can't like provide a type definition. You can only provide a function that whose image is exactly that type. So like if you have this is like if I write something like a function whose domain is any noun, whose image is exactly ABC, this is actually a type definition because it has because it has because it's a function with any noun as the domain and some specified image. I actually get a type failure here, right? I needed ABC and I had DEF. That's the only way that you can provide types, and this is a very runtime oriented as well, so you can actually pretty easily pass type data over the network. Use these special operators. Vasing, it just produces. You give it some value, which since you're compiling Hoon, it's typed, and it gives you at runtime the cell of the type and value, just as a noun. It's like there's no magic here. It's literally just saying this is Adam UD and then 1 2 3. And you can just send this over the network or whatever. This is sent over the network all the time. On the other end, let me assign this to a name. So this is called V now. At the other end, you need to provide something for it to nest into, and this will type check it at runtime just by invoking the type checker. You can type fail there if the type being passed around at runtime doesn't match. So like this is because this is an interactive system, right? You have the type checker available at runtime. So I'm asking, does void nest in noun? So is void a subtype of noun? The answer is trivially yes. Is unsigned decimal atom. But does unsigned decimal atom nest in generic atom? Yes, but 7-bit ASCII, no. So that's just part of the compiler that enforces subtyping rules and also be used in a runtime type check like the above. Okay, there's obviously many other parts in the paper that cover different facets of the system, like how it bootstraps itself into an operating system, which I've chosen not to cover because that would take quite a bit longer time. I just wanted to focus on the Nock VM mainly because I think it could be applicable to other VM projects or other things that want to compile to compiler to combinator machines and so on. So I've covered basically everything that I wanted to cover. Be happy to take questions, especially since that went to a lot of places probably fairly quickly.
Yeah, I have one. So when you were looking at the type of, I believe noun, it was like 2 billion or something like that. How does it encode that like uniquely? Do you just send it over the network and get to say, well, this thing is an atom type? Because it looked like when you looked at it, it was like 2 billion, something like that. I forget the exact expression you wrote.
It would have been a few million. You're
Yeah,
talking about this, right?
yeah, I believe so. Yeah, that.
Yeah, and I mean this is literally just uh, that's literally just the word atom, right? So it's four bytes.
Oh, I
Um,
see.
how do we send these over the wire? Because these are like constels. The answer is jam. We can turn any noun of any complexity. There's a specified way, one-to-one invertible way to turn it into an atom, which then we can just use as bytes and send as bytes over the wire. So what we actually do to send type data over the wire, like our type data is 123. First, you vase it, so you const it with its type. At runtime you const it with its type, and then you jam it. It's going to take forever to pretty print, so I'll just list how many bytes this is. But this is 11 bytes here. Okay. It's only 11 bytes. It might not take. Yeah, it won't take forever to pretty print. Usually they're a bit more complex, especially if they contain like recursive types or cores or so on. So you have to do a bit of deduplication on large things. The actual wire protocol is more complicated, but conceptually, all you do is like jam. So like your packet it happens to be 11 bytes, and then what you do at the receiving end, you queue it back into a noun, which is totally untyped. You can devase it with the type you expect. I'll just expect a generic atom. So I've screwed something up here. Not sure exactly what, but yeah, morally that's what you do. Because you can always have something untyped with its type at runtime, and you can always go back and forth between just some bytes or an atom, which is trivially interpretable as some bytes.
Nice. Yeah.
So Ray, I think you said a type was like a function. It's an
Yeah.
image. So can you encode types like is even or something like that? So have a check, like a runtime check in the image of the function.
You can actually make this, but like it's not the type checker is not going to enforce the evenness of it specifically, right? It's not like a dependent type checker. It's just a
Right.
it's just a sort of standard type checker. So it'll enforce like, is it an atom, or it'll enforce things about constants, because those have like a unique type each. So like you can have simple things like, a tagged union, right? You have a tagged union, either an atom or a cell prefixed by whether it's an atom or a cell. As to that, like you have like a tagged union type like that, for example, and then you can branch on this. You can what you can do is enforce runtime constraints this way, right? Like you can encode something that had as a mold. These like type defining functions are called molds because they sort of take a noun and pour it into a mold. But you can enforce these constraints at runtime by invoking the mold, which some code does this, like, right? Usually you use these bespoke syntaxes like all these $sign syntaxes, like this bucksen here is a simple way to define a tagged union, and use these rather than directly writing functions. But if you choose to directly write a function, then you can use it at runtime. You won't get it from the type checker, so you won't get it at compile time, but it's available. And like any you won't be more lenient than the type checker running against this will provide. You will only be less lenient because of things the type checker cannot check. Given like a smarter inferencer that knew about things like that, you could potentially extend it into a system that knew how to do things like that.
So you can still enforce like types at runtime. So like if you're getting like some data over the network, you could basically check that the packet that's coming in is even, and is even example with the type checker, and then like probably dispatch based on the fact that
doing it at runtime. Doing it at runtime, you have to mold that. You like usually you mold it through the mold, which is code, just of some defined thing, just of some defined shape. Like it's just has to accept any noun and produce just nothing. So every type does have a default value. This comment is a bit out of date in the sense that currently it's considered better for them to be non-total. So like if I have a mold called Atom, I think there's or I can just use the at syntax, which is the syntax for the mold of Atom. Like currently it's considered better to have these be non-total. In previous iterations of the language, it would produce the default value of Atom, which is 0. You can use this star syntax to get default values, or a cell is cell of zeros. Currently, it's considered better to have them be non-total because there's a type system hack you can use to turn any non-total mold into a total one. It's just this soft. Because this hack exists, it makes it a bit nicer to have just non-total molds. But both of them are valid language designs.
Well, if that's it for questions, do you have any more presentation you'd like to give, Ray?
See, I mean that's it for now. But I would be happy to give more practical tutorials, or conversely less practical tutorials. In the case of things like designing combinator VMs.
Yeah, I think we could definitely have those in like future weeks of this compilers reading group. I guess I'll mention one thing since it's the holidays coming up. There's gonna be a lot of off time for a lot of us, so the reading group's gonna be on hold for a while. I'll give a sneak peek of what's coming next. It'll probably be the self paper. There's a nice paper about the self language and compiler, and then we could probably intersperse some demonstrations like this alongside general readings like the self paper and whatnot. I think there'll probably be some interesting things coming up in the next coming year, which is when we'll probably resume. I would like to thank everyone for coming out today, and I'd like to thank in particular our presenter Ray for giving the great presentation of Nock. I would not have been able to give this. So I think that's quite nice. And with that, I bid you all adieu.